I'm going to explain here how to use the reduced row echelon form in R for solving system of linear equations. So I will give you the step for solving a system. The first step is write an augmented matrix of the form AB. This A will be the matrix of coefficient. This B, this will be the matrix of the constant terms at the other side of the equation. So it will be something like this. So it will be a matrix when you have all the coefficients. I usually separate this with a vertical line if I'm working by hand. And then at the other side of the line type the constant terms and close brackets. So they will be the matrix that we are going to use. That will be the first step, and then as a second step compute the reduced row echelon form of that matrix. As a third step, you will need to check this reduced row echelon form. If every leading one in this reduced row echelon form is located on the left side of the reduced row echelon form, so it won't be any of the leading ones in the last column. No, everything will be on the left side of this reduced row echelon form. And the number of leading one is the same of the number of unknowns. For example, if you have 3 unknowns, 3 leading one. Remember that the leading one will be the first number that you are going to find different than 0 in every row of the row echelon form. You are going to find some ones. Yeah? So the first one that you find in every row is a leading one. So if this number of leading one is the same of the number of unknowns, then the system has a unique solution. If you have 3 leading ones, no one is in the last column, and you have 3 unknowns, so we have a unique solution. If you have 7 leading ones, none of these ones is in the last column, and you have 7 unknowns also, so we have a unique solution. So in this way, you notice with the reduced row echelon form that the system have a unique solution. And that will be given on the right side of the reduced row echelon form. So the last column of the reduced row echelon form will have the solutions. We can use the same example of the other video, so the same system of equations that we know that is equivalent to this matrix equation. And of course, the first things to do if we are using this technique, so this method, what you are going to do is just type the augmented matrix. The augmented matrix for solving a system of equations. And then at the second step, use a software or something that can help you to compute the reduced row echelon form. Or doing by hand, I explained in another video how to compute the reduced row echelon form of a matrix by hand. But here, so let's use R in this case. So you open R, and again, remember for working matrix algebra, a good package is Pragma. So called Pragma. Remember, you should have Pragma installed before in your system, before solving a problem using Pragma, also, of course. So call Pragma, so you type library, open bracket, and open quotation and Pragma. Close quotation, close bracket, and then enter. When you enter, R is ready to accept any operation, to make any operation using Pragma. Especially one that is important is the reduced row echelon form of the matrix. So let's enter the matrix first, and the matrix is this matrix. I'm going to call it A, this matrix, but you can have any name. So let's call it A, open bracket, and matrix, open bracket, C2, 4, 1, 4, 3, minus 3, minus 5, 10. And don't forget, after you close the bracket, for the combination argument, so this bracket, type the number of rows and the number of columns. In this case, we have 3 rows, 4 columns for the augmented matrix. So now I know what is the matrix that needs to compute the reduced row echelon form. So press enter and this matrix will be in the memory of R and will appear this symbol here. That means R is ready for you to enter any command or any operation. In this case, what I'm going to do is compute the function reduce row echelon form of A. So RREF of A and press enter. When you press enter, R give you the solution of the reduced row echelon form of the matrix. And I noticed that there is no leading one in the last column, and I also noticed that the number of leading ones is exactly the same number of unknowns. Then this system has a unique solution, and the solution appears here on the last column, 1 1 minus 0.2. So I'm going to say then that the solution is x1, x2, x3 equal 1 1 minus 0.2. We say that x1 equal 1, x2 equal 1, and x3 is minus 0.2, negative 0.2. And that is the way that we solve a problem in which we have a unique solution. So if we have a unique solution, now we are going to analyze other cases. Let's analyze now a second case. Again, for solving a system of linear equations using the reduced row echelon form, do always the same. The matrix of coefficients and the vector of constant form an augmented matrix. And second, use a reduced row echelon form, or find the reduced row echelon form of this augmented matrix. After you have that, if there is a leading one located in the last column of the reduced row echelon form, then the system does not have solution. The system doesn't have a solution in this case. For example, you have this matrix, these systems of equation, negative 2x plus 8y plus 3z equal 14, 6x minus 8y plus 2z equal negative 18, 8x plus 10z equal 2. This will be equivalent to this matrix as a matrix A minus 2a3, the coefficients that are in the first equation. Then in the second equation, 6 minus a2 are the coefficients, so they will be the entries in the second row of the matrix A. And finally, here in the third equation, we observe that doesn't appear a term for y, the second of the unknowns. So this means that this coefficient will be 0. So it will be a0, 10. That multiply the vectors of unknowns, that in this case will be x, y, and z. And this will be equal to the vector of the constants, 14 minus 18 and 2. So this is the equation, and actually what we are going to do is construct the augmented matrix for this system. And the augmented matrix will be, of course, having to the left side of the matrix to the matrix of the coefficients, and then as the last column, the vector of constant, 14, 8, negative 18, 2, and close bracket. So this is the one that we are going to use in R. Then, as a second step, open R. And when you open R, obviously, if you haven't called pragma in your session, call pragma. So that will be the first step. We are going to be using pragma, that we know that will be the package in R that allow me to compute the reduced row echelon form. So call library, and then in quotation pragma, press enter. After you press enter, you see this symbol, means R is ready for you to enter whatever command or whatever operation you want. And obviously in this case, you need to enter first the augmented matrix. You need to put a name to this augmented matrix. Let's call it A. So I call A equal matrix and all the columns, minus 2, 6A, etc. until the last column, 14 minus 18, 2. Don't forget to tell R number of rows, number of columns. In this case is the matrix that have minus 2, 6a, a negative a, 8, 3, 2, 10, 14, negative 18, 2. Let's finish here and then tell it will be 3 rows, 4 columns. There are several ways to combine these 12 entries. Could be 2 rows, 6 columns, for example, or 6 rows, 2 columns, or 4 rows, 3 columns. That you need to tell there are 3 rows, 4 columns. And after you have that, then press enter. Now R is ready to compute whatever things that you can do now, including things for the matrix A. And what you are going to do is compute the reduced row echelon form of A. So just compute reduced row echelon form of A. So let's do it. Just type reduced row echelon form of A, RREF of A, and press enter. If you press enter, R immediately make a computation. You see here that there is 1, 1, 2, and 3 leading ones, but this leading one is in the last column. Always the first element in the row will be a 1 in a reduced row echelon form in R. And this one appears here in the last column. So this means that the system doesn't have a solution. Your answer must be the system does not have solution. Let's see the last case. The last case will be the case when the system have infinite solutions. So let's review this last case. If there is no leading one in the last column, and number of leading ones in the reduced row echelon form is lower than the number of unknowns, then the system has an infinite number of solutions. For example, if we have this system, minus 2x plus ay plus 3z equal 14, then another equation, 6x minus 7y plus 2z equal negative 16, and finally 12x plus 3y plus 15z equal negative 6. As always, these systems of linear equations is equivalent to one matrix equation, this one. So, in which we have the matrix of coefficients, a vector of unknowns, and the vector of constants at the other side. So as the first step, write the matrix, the augmented matrix, in this form, A, B. So coefficients, first step, the coefficient, the matrix of coefficients, then I draw a line if I'm working by hand, and then just to recognize what elements are in the last column, 14, negative 15, 6, that are the elements in the vector of constant, and close the brackets. That will be the steps if I'm working by hand. Actually, if I'm working with R, I can from the beginning type what is the augmented matrix. I know that the augmented matrix will be the matrix of coefficients, and the last column will be the vector of constant. Let's do the second step, but I'm going to do it using R. So I'm going to open R, and obviously if I haven't called pragma in the section I'm working, so I will be calling pragma. I'm going to call pragma here because I'm just starting R. So I call pragma and I type library, and then after library in quotation pragma, and press enter. If you do that, R is ready for you to enter anything, and what I'm going to do is just enter the augmented matrix. So the augmented matrix, A matrix, C for combine, and all the columns, one by one, separated every entry by comma. Then at the end, the number of rows and the number of columns. And press enter. Now R is ready to compute the reduced row echelon form. The only that you need to do is type RREF of A. So A in bracket. So anytime the argument you notice in R is in bracket. And now that you press this, you can press enter. If you press enter, R give you the solution, the reduced row echelon form. When I see the reduced row echelon form, I notice that there will be only two leading ones. You see this one and this one. And there is no leading one at the other side. There is no leading one in the last column. Because if there is a leading one in the last column, then the system doesn't have a solution. But in this case, there is no leading one, and also the number of leading ones is lower than the number of unknowns. There are 3 unknowns, but only 2 leading ones. So it means that in this case, the system has infinite solution. And how to write this solution? So it means z, the value of the last variable, the value of z could be whatever real number. So I'm going to type that there is, because there is only 2 leading ones, then we have infinite number of solutions. And what will be the solution? Z will be whatever number. So the last row of the reduced row echelon form shows that z can have any value. So the value of z could be whatever real number, but the value of y depends on this. You can see the last row with leading one. This leading one corresponds to y, so y plus 0.64758 z will be equal to 1.5294118. So you can transform this second row in an equation. So you can type the second row, give you this, that y plus 0.64758 z equal 1.5294118. And this first row give you a value of x, so 1x plus 1.0882353z, because this coefficient appears now in the third column, that will be equal to minus 0.88235229. So let's type this. The first row of the reduced row echelon form shows that x plus 1.0882353z will be equal to minus 0.88235229. So the system have infinite solution. So z can have any value, and depending on the values that z have, that will be the value of y. For example, if z had the value 0, so this will be 0, and y will be equal to 1.5294, etc. And if z is 0, x will be equal to x will be equal to minus 0.88235229. Or for example, if z equal 2, or if z equal 2, then y will be 1.5294118 minus 0.647582. So this number will be multiplied by 2 and will be writing at the other side negative. So it will be this 1.5294118 minus this 0.647588 multiplied by 2. And the value of x then will be this minus 0.88235229 minus this number 1.0882353 multiplied by 2. In this case, we can use a calculator to compute y, and this will be equal to 0.2352942. And the value of x, if you make a substitution, x will be multiplying this by 2 and make a subtraction here, minus 0.88235229 minus this, it will be minus 3.058825. And that shows you how to find each of the solutions. But the infinite solutions are given in this general way. The 3, z can have any value, y must satisfy this equation, and x must satisfy this equation. And if you want to know a special value, give a value of z and you will be finding values for y and x. Okay, so that finished the explanation of the third and last case. So the system can have a unique solution, no solution, or infinite solution. And in each case, you can notice that with error. So with this, I finish my explanation. Please don't forget, you will need to download Pragma first in your R for working in your R. Pragma is a package that you will need to have in R before solving this type of problem. Okay, I think I haven't finished explaining this. If you find it useful, please subscribe to the channel and make comments that will be helping other students. Thank you.